Good evening. Tonight, you'll discover islands of billions of stars, spinning slowly through the cosmic void, structures so vast they take light millions of years to cross. 100 facts about galaxies that will carry you gently into sleep. But first, if you want more peaceful journeys like this, subscribe to the channel and leave a like right now, because in just a few moments, you'll be far too relaxed to move. Now then, make yourself comfortable. Let the tension leave your shoulders. Close your eyes. Tonight, I invite you on a voyage through space and time, through spiral arms and elliptical clouds, through the vast cosmic web that connects everything. 100 remarkable facts, told slowly, gently, without haste. You don't need to remember them. You don't need to understand the mathematics. Just listen, and let these words become the backdrop to your dreams. Breathe evenly, deeply, and we begin. A galaxy is an enormous collection of stars, dust, gas, and dark matter, all bound together by gravity. Think of it as an island of light, floating in an ocean of darkness. Our own galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. That's billion, with a B. And each of those stars could have planets, could have moons, could have worlds we'll never see. The sheer scale is almost impossible to comprehend. If each star were a grain of sand, you could fill an entire Olympic swimming pool with just the stars in our galaxy alone. It's humbling, really, to realize how small we are, how vast the cosmos truly is. The word galaxy comes from the Greek word galaxias, which means milky. The ancient Greeks looked up at the pale band stretching across the night sky and thought it looked like spilled milk, a river of milk flowing through the heavens. They didn't know, couldn't have known, that they were seeing their own galaxy from the inside. Billions of stars, so distant they blurred together into a soft glow. They created myths about it. One legend said it was milk from the goddess Hera, sprayed across the sky. It wasn't until Galileo turned his telescope skyward in 1610 that we realized the truth. That pale band was made of stars, countless stars. There are approximately 2 trillion galaxies in the observable universe. 2 trillion. That's 2,000 billion. If you tried to count them all, one per second, it would take you more than 63,000 years. And each of those 2 trillion galaxies contains millions or billions or even hundreds of billions of stars. The numbers become so large, they lose meaning. They become poetry instead. Just imagine if every person on Earth were assigned their own galaxy. There would be enough for everyone to have about 250 each. The universe is larger than our minds can truly grasp. Galaxies come in different shapes. Some are spiral, with elegant arms curving outward from a bright center, like cosmic pinwheels, slowly turning. Others are elliptical, round or oval, with no distinct structure, just a smooth glow of ancient stars. Still others are irregular, chaotic, shaped by collisions or gravitational interactions. Galaxies that haven't yet settled into a stable form. And then there are the peculiar galaxies, the strange ones, the ones that don't fit any category. Nature's experiments. Our galaxy, the Milky Way, is a barred spiral galaxy. That means it has a bar-shaped structure of stars running through its center, with spiral arms extending from the ends of the bar. From above, if you could somehow float above our galaxy, it would look like a cosmic Catherine wheel, beautiful, symmetrical, slowly rotating. The bar itself is about 27,000 light-years long, a straight structure of older stars cutting through the galactic center. But we can never see it from outside. We're trapped inside, forever looking at our home from within, like trying to see the shape of a forest when you're standing among the trees. Interesting, isn't it? The Milky Way is about 100,000 light-years across. A light year is the distance light travels in 1 year. At 186,000 miles per second, that's about 5.8 trillion miles. So the Milky Way is, let's see, 100,000 times 5.8 trillion. That's 580 quadrillion miles across. If you started driving across the galaxy at 60 miles per hour, never stopping, it would take you about 1.1 billion years to reach the other side. You might want to pack snacks. Despite being so vast, the Milky Way is actually spinning, rotating like a giant cosmic wheel. At our location, we're moving at roughly 515,000 miles per hour, and yet we feel nothing. We live in one of the spiral arms of the Milky Way. It's called the Orion Arm, or sometimes the Orion Spur, a minor arm between two major ones. We're about 26,000 light-years from the galactic center, roughly halfway out, in the suburbs of our galaxy, a comfortable place to be. Not too close to the crowded, dangerous center, but not too far out in the lonely edges. The inner regions are chaotic, stars packed close together. The supermassive black hole dominates, too turbulent for life. But here, in the middle, conditions are just right. The Milky Way is on a collision course with the Andromeda Galaxy. Don't worry, the collision won't happen for another 4.5 billion years. You have time. When it does happen, when these two giant spirals finally meet, they'll pass through each other. Stars are so far apart that actual collisions will be incredibly rare, but gravity will twist and warp both galaxies. They'll dance around each other, merge, become one. Astronomers have already given this future galaxy a name, Milkomeda. Computer simulations show the two galaxies approaching, their spiral arms stretching toward each other. The first pass will be dramatic, then they'll loop back and collide again, over billions of years, until they settle into a single giant elliptical galaxy, if you're still not asleep. The first galaxies formed about 13 billion years ago. The universe itself is 13.8 billion years old, so galaxies are nearly as old as time itself. In the beginning, in those first few 100 million years after the Big Bang, there were no galaxies, just clouds of hydrogen and helium, darkness, fog. Then, slowly, gravity began to pull matter together. The first stars ignited, and those stars began to cluster, to gather, to form the first galactic structures. These first galaxies were small, chaotic, nothing like the grand spirals we see today, but they were the seeds, the beginning of everything that would come after. The most distant galaxy we've ever observed is called GN-Z11. It's so far away that when we look at it, we're seeing light that left the galaxy 13.4 billion years ago. We're looking back in time, seeing the universe as it was just 400 million years after the Big Bang. That galaxy, those stars, might not even exist anymore. We're seeing a ghost, an echo of the ancient past. The light has been traveling through space for so long that the universe has expanded significantly since it began its journey. What we see is a snapshot of the distant past, frozen in time. Early galaxies were smaller than modern ones. They were irregular, chaotic, still forming, still gathering matter. Over billions of years, These small galaxies merged, combined, grew larger. The Milky Way itself has absorbed dozens of smaller galaxies over its lifetime, consumed them, made them part of itself. Even now, we can see the remnants of these ancient meals, streams of stars that once belonged to other galaxies, stretched across the sky like cosmic rivers, evidence of our galaxy's cannibalistic past. The oldest stars in our galaxy are about 13.2 billion years old. They're found in globular clusters, dense spheres of ancient stars orbiting the galactic center. These stars formed before the Milky Way had a disk, before it had spiral arms. They're older than the structure of our galaxy itself. When you look at them, you're looking at some of the first stars ever born, witnesses to the early universe. They orbit in a halo around the galaxy, moving in random directions, not following the orderly rotation of the disk. Ancient wanderers, following paths set billions of years ago. Galaxies grow through two main processes: mergers and accretion. Mergers, when two galaxies collide and combine, becoming one. Accretion, when a galaxy slowly pulls in gas and dust from its surroundings, building up gradually, like snow accumulating on a mountainside. Both processes are still happening today. The universe is not static. It's constantly changing, evolving. The Milky Way is currently accreting gas from the intergalactic medium, slowly adding to its mass, building itself up, grain by grain, atom by atom. When galaxies collide, spectacular things happen. The collision triggers massive bursts of star formation. Gas clouds compress, heat up, ignite. New stars are born by the millions. The galaxies light up like cosmic fireworks. These are called starburst galaxies. Galaxies in the act of creating more stars in a few million years than the Milky Way creates in a billion. Imagine that, 100 times more active than our entire galaxy. The sky would be filled with brilliant young stars, blue giants, supernovae exploding, a spectacular but violent cosmic display. Despite these violent collisions, individual stars rarely hit each other. Space is mostly empty. Stars are tiny points in an ocean of vacuum. When two galaxies merge, they pass through each other like ghosts. The stars slide past, miss each other by light years. It's the gas and dust that collides, the space between the stars, not the stars themselves. Even in the densest part of a galaxy, stars are separated by distances millions of times their own diameter. The odds of two stars actually colliding are vanishingly small, almost impossible. Spiral galaxies are the most iconic type. They have a central bulge, surrounded by a flat, rotating disk, with spiral arms curving outward. These arms are regions of active star formation, where gas clouds collapse. When new stars are born, the arms glow blue with young, hot stars, while the central bulge glows yellow and red with older, cooler ones. The spiral pattern isn't fixed. It's not like the arms of a solid pinwheel. Instead, the pattern is a density wave, a wave of compression moving through the disk. Stars drift in and out of the arms, but the pattern persists. About 60% of nearby galaxies are spiral galaxies. They're common in the modern universe. Beautiful, structured, dynamic, but they weren't always so common. In the early universe, irregular galaxies dominated. Spirals formed later, as the cosmos settled down. It takes time for a galaxy to develop spiral structure. The disk must form. The rotation must stabilize. Order must emerge from chaos. Perhaps billions of years of evolution. Elliptical galaxies are shaped like ellipsoids. They can be nearly spherical or stretched out like footballs. They have no disk, no spiral arms, No clear structure, just a smooth, diffuse glow. A cloud of stars. They range from small dwarf ellipticals, containing just a few million stars, to giant ellipticals containing trillions. The giants dominate the centers of galaxy clusters, ancient and massive. Elliptical galaxies contain mostly old stars. They've used up most of their gas. They're no longer forming new stars. They're aging, slowly fading. The stars within them are old, red, cool. These are galaxies past their prime, but they can be enormous. The largest galaxies in the universe are elliptical, giant ellipticals, containing trillions of stars. Some of these giants formed through multiple mergers. Dozens of galaxies, consumed over billions of years, growing larger with each meal. Cosmic cannibals at the centers of galaxy clusters. Many elliptical galaxies form through galactic mergers. When two spiral galaxies collide, the collision scrambles their structure, destroys their disks, mixes their stars. What remains is often an elliptical galaxy, the remnant of a cosmic collision. This is what will happen to the Milky Way and Andromeda. After they merge, they'll likely form a giant elliptical. All the beautiful spiral structure, gone. The ordered rotation, disrupted. Stars thrown into random orbits. A new galaxy, born from the destruction of two old ones. If you're still listening, irregular galaxies have no defined shape. They're chaotic, asymmetric, often caused by gravitational interactions or mergers. They're common among dwarf galaxies, small galaxies, young galaxies. They haven't had time to settle into a stable configuration, or they've been disturbed by a close encounter with another galaxy. Their stars and gas are still finding equilibrium, still organizing themselves. The large and small Magellanic Clouds are irregular galaxies. They're satellite galaxies of the Milky Way, orbiting our galaxy like moons around a planet. From the southern hemisphere of Earth, you can see them with the naked eye. Two fuzzy patches of light. Beautiful, ethereal. They're named after Ferdinand Magellan, the explorer who observed them during his voyage around the world. The Magellanic Clouds are slowly being torn apart by the Milky Way's gravity. In a few billion years, they'll be completely absorbed, becoming part of our galaxy, their stars, joining ours. Lenticular galaxies are intermediate between spiral and elliptical. They have a disk, like a spiral galaxy, but no spiral arms. The disk is smooth, featureless. They're transition objects, galaxies that have used up their gas, but haven't yet been transformed by a major merger. In between, neither one thing nor another. They often have large central bulges, and like ellipticals, they contain mostly older stars. Their star-forming days are largely over, but they retain the disk structure of their spiral past. Some galaxies are called ring galaxies. They have a ring-like structure, a circle of stars and gas surrounding the galactic center. These unusual structures often form when a smaller galaxy passes through the center of a larger disk galaxy. The collision sends a wave rippling outward, like dropping a stone in a pond. The wave becomes a ring, a cosmic echo of an ancient encounter. The ring is usually a region of intense star formation. The collision compressed the gas, triggering the birth of millions of new stars, a circular nursery of blue giants glowing brightly. At the center of most large galaxies lies a supermassive black hole. Supermassive, millions or billions of times the mass of the Sun. The Milky Way has one. It's called Sagittarius A star, pronounced Sagittarius A star. It has a mass of about 4 million suns, compressed into a space smaller than the orbit of Mercury. Despite its enormous mass, it's relatively quiet. not actively consuming much material, just sitting there, a sleeping giant at the heart of our galaxy, waiting. Supermassive black holes don't suck in everything around them. They're not cosmic vacuums. They follow the same laws of gravity as everything else. If the Sun were suddenly replaced by a black hole of the same mass, Earth would continue orbiting exactly as before. Nothing would change. Well, except for the lack of sunlight. That would be a problem. Black holes only pull in matter that gets too close. That crosses a boundary called the event horizon. Beyond that boundary, you can orbit safely, just like planets orbit stars. The stars near Sagittarius, a star at the center of our galaxy, orbit it just like Earth orbits the Sun. Some complete their orbits in just a few years, racing around the black hole at incredible speeds. Some galaxies have incredibly active centers. These are called active galactic nuclei, or AGN for short. They occur when material falls into the supermassive black hole at the galaxy's center. As matter spirals inward, it heats up, becomes incredibly hot, millions of degrees. This hot material releases enormous amounts of energy, more energy than all the stars in the galaxy combined. Active galactic nuclei can outshine their entire galaxy, a single point of light, brighter than 100 billion stars. Quasars are the most luminous type of active galactic nucleus. The word quasar is short for quasi-stellar radio source. When they were first discovered, astronomers thought they were strange stars, but they're not stars. They're supermassive black holes, feeding voraciously, shining across the cosmos. The most powerful quasars can be 1,000 times brighter than the entire Milky Way. A single black hole, outshining a galaxy. They're mostly found in the distant universe. In the past, when the universe was young and galaxies were still growing, back then, there was more gas available, more fuel for the black holes. The universe was more active, more violent, more energetic. Some black holes produce jets, powerful jets of particles and radiation, shooting out perpendicular to the accretion disk, extending for thousands of light years into space. These jets move at nearly the speed of light. They're among the most powerful phenomena in the universe. We don't fully understand how they form, how the black hole launches these cosmic fountains, but they're beautiful, spectacular. Beacons visible across the universe. The jets are powered by the black hole's rotation and magnetic fields. Somehow, the black hole takes the energy from infalling matter and channels it into these narrow beams, cosmic searchlights. The center of our galaxy, Sagittarius, a star, is relatively quiet. It's not an active nucleus, not a quasar, just a sleeping giant. But it does flicker occasionally, flares of X-rays and infrared radiation, brief moments of activity when a small amount of material falls in. Perhaps, long ago, it was more active. Perhaps it had its moments of glory. And now, it rests, waiting, patient. Scientists observe stars orbiting very close to it. Some complete their orbits in just 16 years, racing around the black hole at incredible speeds. These observations help us understand the black hole's mass and properties, if you're still awake. Not all galaxies are giant spirals or massive ellipticals. Many are small, dim, containing only a few billion stars, or even just a few million. These are dwarf galaxies, the little siblings of the galactic family. They might seem insignificant, but they're important. They outnumber the large galaxies, and they might hold clues about dark matter, about galaxy formation, about the early universe. Dwarf galaxies are actually the most common type of galaxy in the universe. For every large galaxy like the Milky Way, there might be dozens or even hundreds of dwarf galaxies. They're just harder to see, fainter, easier to overlook. But they're everywhere, orbiting larger galaxies, drifting through the cosmic voids, hiding in plain sight. In fact, there are probably many dwarf galaxies we haven't discovered yet, too faint to detect with current telescopes. Invisible neighbors, waiting to be found. The Milky Way has dozens of satellite galaxies, small galaxies orbiting our own, bound to us by gravity. The largest are the Large and Small Magellanic Clouds, visible from the southern hemisphere. Beautiful irregular galaxies, slowly being pulled apart by the Milky Way's gravity. Others have names like Draco, Ursa Minor, Sagittarius, named after the constellations where they appear. Some are so faint, they were only discovered in the last few decades. As our telescopes improved, we found more and more of these dim companions, each one a small galaxy, quietly orbiting in the darkness. Some dwarf galaxies are called ultra-faint dwarfs. They're so dim, they contain fewer stars than a typical globular cluster, just a few thousand stars. They're almost invisible, nearly impossible to detect. We only find them through careful surveys, patient searching, but they're important. They might contain clues about dark matter, about galaxy formation, about the early universe. Sometimes, the smallest things hold the biggest secrets. These ultra-faint dwarfs are dominated by dark matter. Almost all their mass is invisible. The few visible stars are just tracers, markers of a much larger dark structure. Dwarf galaxies are often rich in dark matter. In fact, proportionally, they contain more dark matter than regular galaxies. Some dwarf galaxies are almost entirely dark matter, with just a few stars visible, like cosmic ghosts, barely there. This makes them valuable for studying dark matter, for understanding this mysterious substance that makes up most of the universe's mass. By observing how stars move in these dwarf galaxies, scientists can map the distribution of dark matter, can test theories, can search for answers to one of physics' greatest mysteries. The Sagittarius dwarf elliptical galaxy is being torn apart by the Milky Way. Right now, as we speak, it's orbiting our galaxy. But each orbit brings it closer. The Milky Way's gravity is pulling it apart, stripping away its stars. Long streams of stars stretch across the sky, the remnants of this dwarf galaxy, being absorbed, consumed. In a few billion years, it will be gone completely, merged with the Milky Way, becoming part of us. Some of the stars in our night sky might have once belonged to the Sagittarius dwarf, immigrants from another galaxy, now citizens of our own. Some scientists think dwarf galaxies might have been the building blocks of larger galaxies. In the early universe, small galaxies formed first. Then, over time, they merged, combined, built up into larger structures. The Milky Way itself might be made from hundreds of ancient dwarf galaxies, all merged together, all combined into one. We are, in a sense, made of smaller galaxies, a cosmic amalgamation, a union of many into one. This is called hierarchical structure formation. Small things combine to make larger things, which combine to make even larger things, from atoms to stars, to galaxies, to galaxy clusters, building up, level by level. Interesting, isn't it? Galaxies are not evenly distributed throughout the universe. They cluster together, form groups, gather in communities. Just as stars cluster into galaxies, galaxies cluster into larger structures. It's structure all the way up, from planets orbiting stars, to stars in galaxies, to galaxies in clusters, to clusters in superclusters. The universe is hierarchical, organized on every scale. The Milky Way is part of a small group called the Local Group. It contains about 80 galaxies. Most of them are dwarfs, faint, small. The three largest members are the Milky Way, Andromeda, and Triangulum, the giants of our neighborhood. Together, we're all bound by gravity, orbiting a common center, a cosmic dance that will continue for billions of years. The Local Group spans about 10 million light years. It's our galactic neighborhood, our corner of the universe. Everything nearby that we can consider local. Galaxy clusters can contain hundreds or even thousands of galaxies, huge collections, bound together in a relatively small region of space. The nearest large cluster to us is the Virgo cluster, about 50 million light-years away. It contains over 1,000 galaxies. At the center of the Virgo cluster sits a giant elliptical galaxy called M87, one of the most massive galaxies in the nearby universe. M87 contains about 1 trillion stars. That's more than twice as many as the Milky Way. And it has over 15,000 globular clusters orbiting it. For comparison, the Milky Way has only about 150. In 2019, scientists captured the first image of a black hole. It was the supermassive black hole at the center of M87, the galaxy at the heart of the Virgo cluster. The image showed a ring of light surrounding a dark shadow, the shadow of the black hole itself. It was a historic moment, the first time we'd ever directly seen, a black hole. Something that was once purely theoretical became visible, real, tangible. The black hole in M87 has a mass of 6.5 billion suns. Its event horizon, the point of no return, is about 20 billion kilometers across, larger than our entire solar system. Galaxy clusters contain not just galaxies, but also hot gas, incredibly hot gas, tens of millions of degrees, so hot it glows in X-rays. This gas fills the space between galaxies. It's left over from the formation of the cluster, from ancient collisions and interactions. In fact, there's more mass in this hot gas than in all the visible stars in all the galaxies in the cluster. Most of the visible matter in a galaxy cluster isn't in the galaxies at all. This hot gas is called the intra-cluster medium. It's so hot because it's falling into the gravitational well of the cluster. As it falls, it heats up, reaching temperatures that would vaporize any solid material instantly. Galaxy clusters are the largest gravitationally bound structures in the universe. They can be 10 million light-years across, containing thousands of galaxies, billions of trillions of stars. And yet, even galaxy clusters aren't alone. They form even larger structures called superclusters. Beyond superclusters, the universe is not bound by gravity anymore. The expansion of space takes over. Things get farther apart, not closer together. A supercluster is a group of galaxy clusters, vast chains and sheets of galaxies, stretching across hundreds of millions of light years. The Local Group is part of the Virgo supercluster, which contains about 100 galaxy groups and clusters, and the Virgo supercluster itself is just a small part of an even larger structure called Laniakea. The structures get larger and larger, clusters in superclusters, superclusters in even larger structures. It's almost dizzying, the scales involved. Laniakea is our galactic supercluster. The name means immeasurable heaven in Hawaiian. a fitting name for something so vast. Laniakea contains about 100,000 galaxies. It spans 520 million light-years across. All of these galaxies, including our own Milky Way, are slowly moving toward a region called the Great Attractor, being pulled by its gravity. We're flowing through space, part of a cosmic current, moving towards some distant destination. The Great Attractor itself is a gravitational anomaly, a region of space with an unusually high concentration of mass, pulling everything nearby toward it, including us. We're moving at about 600 kilometers per second in that direction. Between the superclusters lie cosmic voids, vast regions of space, nearly empty, with very few galaxies. These voids can be hundreds of millions of light-years across. They're the largest structures in the universe, bubbles of emptiness in the cosmic foam. If you could somehow stand in the middle of a cosmic void and look around, you might not see a single galaxy in any direction, just darkness, emptiness, the ultimate loneliness. The voids aren't completely empty. There might be a few small galaxies scattered here and there, but compared to the rich clusters, they're almost vacant, silent regions of space. Together, the clusters, superclusters, and voids form what's called the cosmic web. If you could zoom out far enough to see billions of light-years, the universe would look like a web or a sponge, filaments of galaxies, separated by voids, structure on the largest scales imaginable. This is the architecture of the universe, the scaffolding of creation. Beautiful, isn't it? This structure formed from tiny quantum fluctuations in the early universe, microscopic ripples that grew over billions of years into the vast cosmic web we see today, from the smallest scales to the largest. Galactic collisions are surprisingly common. In the crowded environment of galaxy clusters, galaxies often pass close to each other. Sometimes they collide. Even in less crowded regions, over billions of years, encounters happen. Gravity brings galaxies together, choreographs cosmic dances. It's not a question of if, but when. Given enough time, most galaxies will interact with others. The antennae galaxies are a famous example of a collision in progress. Two spiral galaxies, locked in a gravitational embrace, merging together. Long tails of stars stream away from the collision, pulled out by tidal forces. These tails look like insect antennae, hence the name. The collision has triggered intense star formation, billions of new stars being born. The galaxies glow brightly, especially in the regions where gas clouds are colliding. This is what the Milky Way and Andromeda might look like when they finally meet, twisted together, pulling each other apart, creating something new. When galaxies collide, the result is often a starburst, a sudden, intense period of star formation. The collision compresses gas clouds, triggers collapse, ignites new stars, millions of stars, born in just a few million years. The galaxy lights up like a cosmic firework, but this burst cannot last forever. Eventually, the gas runs out, the starburst fades, and what remains is often a quiet elliptical galaxy. The collision uses up the fuel, burns through the galaxy's reserves. A brief moment of brilliance, followed by a long, slow fade into old age. The mice galaxies are another colliding pair, named for their long, thin tails, like the tails of mice. They're about 300 million light-years away. In the constellation Coma Berenices, the collision has been going on for hundreds of millions of years, and it will continue for hundreds of millions more. These are slow dances, played out over cosmic timescales. To us, they appear frozen, a snapshot of a moment. But if we could watch in time-lapse, over millions of years, we'd see them swirl around each other, merge, transform. Some galaxies collide multiple times. They pass through each other. Then gravity pulls them back. They collide again and again. Each passage strips away more stars, more gas. The galaxies become more intertwined. Eventually, they settle down, merge completely, become one. It's like a cosmic courtship, circling each other, coming together, separating, coming together again, until finally, they unite. Two become one. The merger of the Milky Way and Andromeda has already begun. Even though they're still 2.5 million light-years apart, they're already affecting each other gravitationally. Andromeda is approaching at about 110 kilometers per second, getting closer every second. In about 4.5 billion years, the collision will begin in earnest. The two galaxies will pass through each other, then loop back, collide again. It will take another few billion years, but eventually, they'll merge completely. By that time, the Sun will be nearing the end of its life. Our planet, if it still exists, will witness one of the most spectacular events in galactic history. Two ancient spirals becoming one, if you're still listening. Our Sun will likely survive the merger. It will be thrown into a new orbit, perhaps closer to the galactic center, perhaps farther out, but it will survive, and so will Earth. The chances of our solar system actually colliding with anything are astronomically small. We'll have a new view of the night sky though, a different arrangement of stars, new constellations. The children of that distant future will see a sky we cannot imagine. Instead of the Milky Way's pale band, they might see the glow of Milkomeda, a giant elliptical galaxy, filling the sky with the light of 1 trillion suns. Most of the mass in a galaxy isn't in stars. It's not in planets, not in gas, not in dust. It's in something we call dark matter, an invisible substance that doesn't emit light, doesn't absorb light, doesn't interact with light at all. We can only detect it through its gravity. Dark matter is one of the greatest mysteries in science. We know it's there. We can measure its effects, but we don't know what it's made of, what particles compose it, how it came to be. Dark matter makes up about 85% of the matter in the universe. Everything we can see, all the stars, all the galaxies, all the gas and dust, that's just 15%. The rest is dark, hidden, mysterious. Think about that for a moment. Everything we've ever observed, every star, every planet, every nebula, is just a tiny fraction of what's actually out there. The universe is mostly invisible. We're surrounded by something we cannot see, cannot touch, cannot directly detect, and yet it's there, holding everything together. We know dark matter exists because of how galaxies rotate. The outer edges of spiral galaxies rotate faster than they should. If the only mass present was what we could see, those outer stars should fly off into space, but they don't. Something invisible is holding them in, providing extra gravity. That something is dark matter. In the 1970s, astronomer Vera Rubin made careful measurements of galaxy rotation. Her observations didn't match the predictions. There had to be more mass than we could see. Her work provided some of the strongest evidence for dark matter. Every galaxy is surrounded by a dark matter halo, a vast sphere of dark matter extending far beyond the visible galaxy. The visible galaxy, all the stars we can see, sits at the center of this halo like a pearl in an oyster. Most of the galaxy's mass is in this invisible halo. The stars are just decoration, the visible part of a much larger structure. The dark matter halo can extend 10 times farther than the visible galaxy. If we could see dark matter, galaxies would look much, much larger. Vast spheres with the stars just a small concentration at the center. We don't know what dark matter is made of. It's one of the biggest mysteries in physics. Scientists have proposed many candidates, exotic particles with names like WIMPs and axions, but so far, despite decades of searching, we haven't detected dark matter directly. It's out there. We know it's there. We can see its effects, but we can't see it itself. A ghost, a shadow, a presence felt but not seen. Experiments deep underground, in abandoned mines, search for the rare interaction between dark matter and ordinary matter. So far, nothing definitive. The mystery remains. Dark matter played a crucial role in galaxy formation. In the early universe, dark matter clumped together first. Its gravity pulled in ordinary matter. The ordinary matter, hydrogen and helium gas, fell into these dark matter wells, condensed, formed the first stars. Without dark matter, galaxies wouldn't exist, stars wouldn't exist, we wouldn't exist. We owe our existence to something we cannot see. Humbling, isn't it? The invisible scaffolding of the universe, the hidden framework upon which everything visible is built. We are children of dark matter, living in a universe we only partially understand. Galaxies come in different colors. Some are blue, some are red, some are in between. The color tells you something about the galaxy's history, its age, its activity. It's like reading the galaxy's biography, written in light, blue for youth and energy, red for age and quietude. Blue galaxies are actively forming stars. The blue color comes from young, hot stars, stars that burn blue and bright, stars recently born. Spiral galaxies tend to be blue, especially in their spiral arms, where star formation is most active. These galaxies are vibrant, alive, creating new stars at a rapid pace. They have plenty of gas, plenty of fuel. They're in the prime of their lives. Red galaxies have stopped forming stars. They've used up their gas. Their star-forming days are over. The stars they contain are old, red giants, cool stars, stars in the autumn of their lives. Elliptical galaxies tend to be red. They're the retirement homes of the galactic world. Peaceful, quiet, no more fireworks, no more drama, just old stars, slowly fading, waiting for the end. The transition from blue to red is called quenching. When a galaxy stops forming stars, we say it has been quenched. This can happen through several mechanisms. The galaxy might run out of gas, or the gas might be heated so much it can't collapse to form stars, or the gas might be stripped away entirely. Sometimes, a galaxy moves through a galaxy cluster. The hot gas in the cluster strips away the galaxy's own gas, like a cosmic wind blowing away the fuel for star formation. The color of a galaxy can change over time. A blue, star-forming spiral can evolve into a red, quiescent elliptical through mergers, through interactions, through the consumption of gas. Nothing in the universe is permanent. Everything changes, even galaxies. They're born, they live, They age, they die. Or rather, they fade, slowly losing their light, slowly cooling, growing old gracefully, or sometimes violently, but always, inevitably, changing. Some galaxies are called green valley galaxies, not because they're actually green, but because in color magnitude diagrams, they fall between the blue and red populations. They're galaxies in transition, moving from active star formation to quiescence. They're in the autumn of their lives, the colors changing, the activity slowing, a moment of change, caught between youth and age. These galaxies are particularly interesting to astronomers. They're in the process of transformation. Studying them helps us understand how galaxies evolve, how they change from one type to another. Not all galaxies follow the normal patterns. Some are strange, unusual, peculiar. These are often the most interesting. They challenge our understanding, make us question our models, force us to think differently. Nature's experiments, showing us possibilities we hadn't imagined. Hoag's object is one of the most unusual galaxies known. It's a perfect ring galaxy, a ring of blue stars, surrounding a spherical core of older yellow stars. And between the ring and the core, almost nothing, a gap. It looks artificial, like something designed, but it's natural, formed through some cosmic accident we don't fully understand. Perhaps a smaller galaxy passed through the center. Perhaps it's the result of a perfectly aligned collision. We're not sure. Hoag's object remains a mystery, a beautiful, symmetrical mystery. The Sombrero Galaxy looks like, well, a sombrero. A bright central bulge, surrounded by a flat disk, seen edge-on. It's a beautiful spiral galaxy about 28 million light-years away. One of the most photographed galaxies in the sky. Its disk contains a prominent dust lane. Dark bands of dust silhouetted against the bright stars behind. The Sombrero Galaxy has an unusually large central bulge and an unusually large number of globular clusters, about 2,000 of them, 10 times more than the Milky Way, ancient stellar cities orbiting the galaxy. Centaurus A is a peculiar elliptical galaxy. It has a dark dust lane cutting across its center, very unusual for an elliptical galaxy. Scientists think it's the result of a merger, an elliptical galaxy that collided with a spiral. The dust lane is the remnant of the spiral galaxy's disk. The collision also triggered intense activity in the central black hole. Centaurus A is one of the brightest radio sources in the sky. It's relatively close, only about 12 million light-years away, close enough that we can study it in detail. See the aftermath of the merger. Watch the black hole feeding. The Cartwheel Galaxy looks like a wheel, with a bright ring and spokes of material connecting the ring to the center. It formed when a smaller galaxy passed directly through the center of a larger disk galaxy. The collision sent a wave rippling outward, forming the ring. It's 500 million light-years away. A cosmic curiosity, a reminder that the universe is full of surprises. The collision happened about 200 million years ago. We're seeing the aftermath. The ring is still expanding, still moving outward, like ripples on a pond, frozen in time, or rather, moving so slowly that to us they appear frozen. Some galaxies have warped disks. Instead of being flat, their disks are twisted, bent out of shape. This usually happens due to gravitational interactions with neighboring galaxies. The gravity pulls on one side more than the other. The disk warps, bends. Our own Milky Way has a warped disk, caused by interactions with the Magellanic Clouds. We live in a slightly bent galaxy, not perfect, not pristine, but beautiful nonetheless. The warp is subtle. You wouldn't notice it from inside. But if you could view the Milky Way from outside, from the side, you'd see the disk isn't quite flat. It curves up on one side, down on the other. A gentle wave, if you're still awake. Ultra-diffuse galaxies are incredibly faint. They're about the size of the Milky Way, but contain only about 1% as many stars. They're so diffuse, so spread out, they're almost invisible. Scientists aren't sure how they formed, how a galaxy can be so large, yet contain so few stars. They're cosmic mysteries, puzzles waiting to be solved. Perhaps they had their gas stripped away early in their lives, before they could form many stars. Or perhaps they formed in unusual environments, low-density regions where star formation was inefficient. We don't know yet. Jellyfish galaxies have long trailing tentacles of gas and stars. These tentacles are stripped away as the galaxy moves through the hot gas in a galaxy cluster. The gas in the cluster is so dense that as the galaxy moves through it, it creates drag, like moving through water. This drag strips away the galaxy's gas, pulls it out into long streams, tentacles, hence the name. They look like cosmic jellyfish swimming through the universe. The stripped gas often forms new stars in the tentacles, creating chains of young blue stars, trailing behind the galaxy like a glowing tail. Beautiful, but also a sign of loss. The galaxy is being stripped, losing its fuel. Galaxies weren't always as they are today. They've evolved, changed over billions of years. The universe itself has evolved from a hot, dense state to the cool, sparse cosmos we see today, and galaxies have evolved along with it. In the early universe, most galaxies were small and irregular, chaotic, disturbed, still forming. The large, well-organized spirals and ellipticals we see today took time to form, billions of years of evolution. The early universe was a violent place, galaxies colliding frequently, merging, growing. It took time for order to emerge, for the beautiful structures we see today to develop. The peak of star formation in the universe was about 10 billion years ago. Back then, galaxies were forming stars at a much higher rate than today. It was the cosmic noon, the universe's most productive era. Since then, star formation has been declining. The universe is aging, slowing down. Galaxies are running out of gas, using up their fuel. The universe is past its prime, still creating stars, but at a slower pace, entering middle age, moving toward old age. Today's universe is more orderly than the early universe. Galaxies have settled into stable configurations. Spirals have formed beautiful arms. Ellipticals have grown massive and smooth. But in the distant future, things will change again. As galaxies continue to merge, as structures grow even larger, the universe is still evolving, still changing. The story isn't over. We're just living in one chapter, one moment in the vast history of the cosmos. The Hubble Deep Field gave us a window into the past. In 1995, the Hubble Space Telescope pointed at a tiny, seemingly empty patch of sky and stared for days. The resulting image showed thousands of galaxies, some nearby, some incredibly distant, the most distant galaxies in that image. Their light had been traveling for billions of years. We were seeing them as they were when the universe was young. It was a revelation. That tiny patch of sky, no bigger than a grain of sand held at arm's length, contain thousands of galaxies, each one a universe unto itself. The image changed our understanding of the cosmos. Every time we look at a distant galaxy, we're looking back in time. Light travels at a finite speed. It takes time to reach us. When we look at a galaxy a billion light years away, we're seeing it as it was a billion years ago. Astronomy is time travel. The telescope is a time machine. The universe is its own history book. Imagine that. Every observation is a glimpse into the past. The farther we look, the farther back we see. When we observe the most distant galaxies, we're seeing the universe as it was in its youth. We're witnessing cosmic history written in light. The universe is expanding. Galaxies are moving away from each other. Space itself is growing. This was one of the most important discoveries in astronomy, made by Edwin Hubble in 1929. He observed that distant galaxies were redshifted. Their light stretched, indicating they were moving away from us. Due to this expansion, distant galaxies are moving away from us faster and faster. Eventually, they'll be moving away faster than the speed of light, not moving through space faster than light, but being carried by the expansion of space itself. When that happens, their light will never reach us. They'll disappear from view forever. Already, there are galaxies we can see now whose light will never reach our descendants. They're slipping beyond the cosmic horizon, fading into unreachable distance. In the far future, observers in the Milky Way will only be able to see our local group. All the other galaxies will have receded beyond the cosmic horizon, their light stretched and redshifted into oblivion. The universe will appear smaller, emptier, lonelier. Future civilizations might look out and think that their small group of galaxies is all that exists. They'll be wrong, but they'll have no way to know. The evidence will have disappeared, carried away by the expansion of space. Imagine living in a universe where you can't see the full truth, where the cosmos hides itself from you. But before that happens, the Milky Way and Andromeda will have merged, forming a single, giant, elliptical galaxy, Milkomeda. The merger will scramble the stars, destroy the spiral arms, create something new. Our descendants, if they exist, will live in a very different galaxy. A galaxy with no disk, no spiral structure, just a vast elliptical cloud of stars. The night sky will look completely different, brighter perhaps, with more stars visible, but unfamiliar, alien. Eventually, star formation will cease. All the gas will be used up, turned into stars, or expelled from galaxies. No new stars will be born. The universe will slowly grow darker as existing stars burn out and die. This won't happen for trillions of years, but it will happen. The universe has a finite supply of fuel, and eventually it will run out. The last stars will be red dwarfs, small, cool stars that burn their fuel incredibly slowly. They can shine for trillions of years, long after the sun has died, long after most stars have faded. The red dwarfs will remain, tiny embers, the last light in the darkness. They'll be the final witnesses, the last remnants of the age of stars. Slowly, one by one, they'll fade, until finally, the last red dwarf flickers out, and the stelliferous era, the age of stars, will end. Eventually, even the red dwarfs will fade. The universe will enter what's called the black hole era. The only significant objects will be black holes, everything else will have decayed, dissolved, disappeared. The black holes will slowly evaporate through a process called Hawking radiation, taking unimaginable amounts of time. A supermassive black hole might take 10 to the power of 100 years to evaporate. That's a 1 followed by 100 zeros. A number so large, it's almost meaningless. Longer than the current age of the universe by factors we can't even comprehend. The final state of the universe might be what's called heat death, a state of maximum entropy, where everything is spread out, uniform, cold, no stars, no galaxies, no structure, just a thin soup of particles, a nearly absolute zero. That's trillions upon trillions of years in the future, a timescale that makes the current age of the universe seem like a blink. It's a melancholy vision, the universe growing cold and dark, but it's also peaceful. No more conflict, no more change, just silence, eternal silence. But that's just one possibility. We don't know the ultimate fate of the universe. We don't know if our current understanding is correct. There could be surprises, unknowns, things we haven't discovered yet. The universe has surprised us before. It will likely surprise us again. Perhaps the expansion will reverse. Perhaps the universe will collapse back on itself. Perhaps something entirely unexpected will happen. We're still learning, still discovering. The final chapter has not been written, if you're still listening. Every atom in your body was forged in a star. The carbon, the nitrogen, the oxygen, all created in stellar furnaces through nuclear fusion. When those stars died, they scattered those atoms into space, into clouds of gas and dust. Those clouds eventually formed new stars and planets, including Earth, including you. We are made of stardust, literally, not metaphorically. The iron in your blood was forged in a supernova. The calcium in your bones was created in a dying star. You are, quite literally, cosmic material, recycled, reformed, given consciousness. We are made of stardust, literally, not metaphorically. The iron in your blood, the calcium in your bones, all created in ancient stars, billions of years ago. You are the universe made conscious, the cosmos looking back at itself. Every breath you take contains atoms that were once inside stars. Every thought you think is made possible by elements forged in stellar cores. We are, all of us, children of the stars, connected to the cosmos in the most fundamental way possible. Life requires certain conditions: stable stars, rocky planets, liquid water, organic molecules. These conditions might be common in the universe, or they might be rare. We don't know yet. The discovery of thousands of exoplanets, planets orbiting other stars, suggests that planets are common. But we don't know how many have the right conditions for life, how many have water, atmosphere, stable climates. The Milky Way might contain billions of potentially habitable planets. Planets in the Goldilocks zone, not too hot, not too cold, just right for liquid water. Planets where life might have emerged, might have evolved, might be looking up at the stars, just like we are. Statistically, it seems unlikely we're alone. With so many stars, so many planets, the odds favor life existing elsewhere. But until we find evidence, we can only wonder, only hope, only search. We haven't found any evidence of extraterrestrial life yet. Despite decades of searching, despite listening for signals, despite looking for signs, the universe remains silent. Maybe life is rare, maybe we're alone, or maybe life is common. But intelligent, technological life is rare. Or maybe they're out there, quietly observing, waiting. We don't know. The silence might mean we're alone, or it might mean we're not listening in the right way, or looking in the right places. The search continues, patient, hopeful, wondering. The search continues. New telescopes, new methods, new technologies. We're looking for biosignatures in the atmospheres of exoplanets, for radio signals from distant stars, for any sign that we're not alone. And perhaps, someday, we'll find an answer. Perhaps someday, we'll know. The James Webb Space Telescope, the Square Kilometre Array, future missions we haven't even imagined yet, all searching, all hoping that somewhere, out there, we'll find a sign, a message, evidence that we're not alone in this vast cosmos. Regardless of whether we're alone, the existence of galaxies is remarkable. These vast structures, these islands of light, born from quantum fluctuations in the early universe, evolved over billions of years into the beautiful spirals and ellipticals we see today. From nearly nothing, from tiny ripples in the fabric of space, came everything: galaxies, stars, planets, life, consciousness, the universe, creating beauty, creating complexity, creating us. Every galaxy has a story, a history of formation, of mergers, of star birth and death, of black holes and supernovae. Stories written in light, in the motion of stars, in the distribution of gas and dust. We're learning to read these stories, to understand the history of the universe, through the galaxies that fill it. Each galaxy is a book, a chronicle, a record of billions of years, and we're just beginning to learn how to read, how to interpret, how to understand the language of the cosmos. The more we learn, the more questions we have. What is dark matter? What is dark energy? How did the first galaxies form? Are we alone? Each answer leads to new questions. Each discovery reveals new mysteries. And that's beautiful. That's what makes science exciting. There's always more to learn, always more to discover. The universe is not a puzzle with a final solution. It's an endless exploration, an infinite journey. Every answer opens new doors, reveals new horizons, invites us deeper into the mystery. Looking at galaxies helps us understand our place in the cosmos. We live on a small planet, orbiting an ordinary star in the suburbs of an average galaxy. One galaxy among trillions. And yet, we're able to understand this, to map the universe, to trace its history, to predict its future. That's remarkable, that tiny, insignificant creatures on a small rock can comprehend the cosmos. We're small, incredibly small, but we're also, in a sense, large. Our minds can encompass galaxies, can imagine the birth and death of the universe, can wonder about our place in it all. The universe is vast, ancient, beautiful, filled with galaxies beyond counting, stars beyond number, worlds beyond imagination. And somewhere, in one tiny corner of one average galaxy, we exist. We look up at the night sky and wonder and explore and dream. We are the universe awakening, consciousness emerging from stardust. And that is the most wonderful fact of all. In all the vast cosmos, across billions of light years, through trillions of galaxies, here we are, aware, conscious, able to contemplate the universe that created us. We are, perhaps, the universe's way of knowing itself, of understanding itself, of appreciating its own beauty. The journey ends here, but the universe continues. Galaxies still spiral, stars still shine. The cosmic dance goes on. I hope these 100 facts have carried you gently toward sleep, toward dreams of distant stars, of spiral arms, of cosmic wonders. Remember, we're all made of the same material as galaxies, the same atoms, the same elements. We're not separate from the universe. We're part of it, connected to everything, from the smallest atom to the largest supercluster. So rest now. Let these thoughts carry you away, and perhaps you'll dream of galaxies tonight.